All right, hello physics fans. We are on one of our last lectures of the semester, and we're going to talk about sort of a strange one because geometric optics has been around for a long time before any of the physics we've been talking about this semester. In fact, Euclid knew about geometric optics. But this semester we're going to, or this hour we're going to try to maybe link together some of the ideas that we've talked about in terms of light as electromagnetic waves and an older style of dealing with light that does help us to understand some important aspects of imaging that were understood long ago, but which continue to be relevant for us. So last time we talked about the electromagnetic spectrum. Now, we talked about how a light wave can be generated by accelerated charges. So if you have accelerated charges, that causes a oscillating electric and magnetic field to be created at the same time, and the electric and magnetic field that propagate outward from that accelerated charge are perpendicular to one another. And if you go and just look at the magnitudes of the electric and magnetic fields, they have to be connected by Faraday's law, and they're connected through c, the speed of light. And remember that c is just a number. It's something like 2.998 times 10 to the 8th meters per second. So light goes fast, but it does not go infinitely fast, and that's why, yeah, I'm sure you've heard about how when you look at the stars, you're sort of looking back into the past. You're not seeing the stars as they are now. You're seeing stars as they were, millions of years ago. So another thing that we talked about is that the types of electromagnetic waves, they're all essentially the same, but they have different effects because they have different lengths. So you can have long waves that are sort of on the order of the length of the Earth, or longer, and those have a very low frequency, long wavelength, low frequency, or you can have gamma rays that are all the way up to the wavelength with the width of an atomic nucleus, and in that case, those have a very, very high frequency. Now, today we're going to kind of go in the opposite direction. Now, we know that light is caused in some sense by waves, but in the geometric optics paradigm, we instead just think about light as going out in all different directions, and instead of thinking about the wavelengths and things like that, we just worry about the direction the light is going and the direction that it gets bent. So, for instance, at a mirror, we can think about this in wave terms. For instance, a silvered mirror, if you have a high enough frequency, the electrons in the silvering of the mirror can't respond quickly enough to the incoming light, and so the mirror will become transparent. So that's a wave-like property of a mirror. But if you go down to lower frequencies where we are more comfortable with our visible light, the stuff that we already know doesn't become invalid. If you have light that hits a mirror, mostly you know that it bounces back. And so the earliest example of this was the law of reflection for mirrors. And if you look at this, what's the idea? Well, if light goes in straight, it comes back straight. But more generally, if light comes in at an angle, and here we're in this geometric optics literature, we usually define angles as being relative to the normal. So what am I doing there? I'm drawing a line that's perpendicular to the interface where the light is changing directions, and then I define an angle relative to that. So there's my angle in, and then my light bounces back off of the mirror, and then I have a different angle here, angle out. And the law of reflection just says angle in equals angle out. Okay, so pretty simple. Now, why is this useful? Well, let's say that I am looking at an object and I want to think about how far behind the mirror does this object appear to me. Well, I can have angle in equals angle out, angle in equals angle out for two different points that of light that both go into my eye. And if you trace those back behind the mirror, that where they intersect is a point just like the point where all of those light rays emanated from on the physical side of the mirror. So we call this a virtual image. The light that's hitting your eye, of course, is, it's real light, but you can't focus that light into being an image over here on the side of the mirror where you're sitting. Your eyes are tracing that back, so you experience that object as being behind the mirror. And so when we have a virtual image, we give that image a position that we say is negative. Okay? So it turns out that we can then go farther and use mirrors. For instance, if you've been out camping, you might have used a campfire stove where the light comes in, and then you use mirrors to focus the light in on a little tin can or something, and that can allow you to cook food. So that would be an example of the power of reflection. Okay, so over here I have reflection. Remember, the rule is angle in equals angle out. So there would be your angle in, and we would draw a line. My line is quite wavy and probably hard to see, but the angle is relative to the normal of that mirror, and then we have some angle out. We also are going to be concerned with the idea of refraction. So refraction is bouncing light, refraction is bent light. So reflection at the interface, you change direction and you bounce off. In refraction, some of that light at this interface, so this could be like a fish tank, between the light coming in and the light going out, some of the light is bounced back, but some of the light is passed through. And you'll notice that when the light passes through, it bends. And it turns out that the reason that it bends is that the speed of the light changes. And if you go through all of the math, ultimately the reason is that the frequency across this interface stays the same, because you can't change that amount of time, that amount of waves per second that are passing the interface. But what changes is the speed and the wavelength. And because the same number of waves fit in a different amount of time, you have to change the direction for that to be occurring. In a medium where the speed of light effectively is slower, the wavelengths shrink up, and in a medium so water, for instance, light would be traveling slower in water effectively, and faster in air. So it's a little confusing, because you'll remember that we said sound travels faster in water and slower in air. So that's quite confusing. Now, what's a little strange here is that, again, just like we did for our mirror, we don't define the angles in refraction with respect to the angle that you might think. The angle that might be easier to draw is the angle between the light ray and the interface. Instead, we draw the angle between the light ray and the normal. The normal is this line that we're drawing perpendicular to the interface, like that. And as we say, in materials, the phase velocity of light can be less than c, as predicted by the index of refraction of the material. So here's some indices of refraction in vacuum. the index of refraction is exactly 1. That just means that if we look at this relationship, v equals c over n, the speed is just c. But if we have something like water, where the index of refraction is right around 1.33, the speed would be the speed of light divided by 1.33. And so if you go through this analysis, and essentially, as I say, the idea is here the wavelengths are bigger, and to keep the same number of wavelengths in the same amount of time while changing the speed, what you have to do is to squish up the wavelengths, and so shorter wavelengths, slower effective phase speed. Okay, so here's our rule. If you have two media, N1 has one index of refraction, N2 has a different index of refraction, so that will tell you about the speeds at which light goes in each material. They should follow Snell's law. So N2 sine of this angle, N2 sine of the angle that light makes at the interface, equals N1 sine of angle 1. So that would be the angle here that light makes at that interface. So to look at this a little more quickly, a little more slowly, let's say that we have two materials where the indices of refraction match. Well, in that case, light has no reason to change any direction, so the angle in and the angle out here would be the same, and you effectively would not have much reflection. But if you have two materials where the index of refraction changes across the interface, you're going to have two things happen. One thing that's going to happen is that part of that wave is going to be reflected, and in that case you're just going to have angle in equals angle out. And in the other case, your angle is going to be bent. So let me see. I want to try to draw a diagram that's helpful here. So if you have two materials, N1 and N2, let's call this N here for air. This would be N is small. And here I would have N for water, and N would be big. Now, if you have a small index of refraction, what does that mean? That means that your phase speed of light there is big. And if you have a big index of refraction, that means that your phase speed of light is smaller. Okay, so big N goes, or small n goes with big speed, big N goes with small speed. That's just because V equals C over N. Okay, now let's look at these pictures and try to understand what's going on. The angle that we're talking about in Snell's law, this angle 1, if you have an angle that is big here, if the V is getting smaller, the angle also gets smaller. And just to be clear, the angle we're talking about is that angle right there. And so here, this would be your N1, V1, angle 1, N2, V2, angle 2. N is a property of the material, V is a property of the light angle. The angle is a property of the bending at the interface. And so that's where we say that N1 sine of angle 1 equals, and then down here we would have index of refraction 2, N2 sine of angle 2. Okay, and so you can see the same thing happening here. If you're going from water to air, here you would start with a smaller speed because you're in water, and then as you exit there, your angle gets bigger because you go from a smaller speed to a bigger speed. So smaller speed to bigger speed means you're going from a smaller angle to a bigger angle. And so that's bending away from the normal. Okay, now here's two little thinking questions. Suppose that you're in a dark room with just one light bulb and a flat mirror. What path do the light rays take if you see yourself in the mirror? Now, I'm not claiming this is a super profound question, but sometimes if you have not thought about it before, it is the sort of question that catches you off guard. So let's say, here's your mirror, here's your light bulb, and you are seeing yourself in the mirror, illuminated ultimately by this light bulb. How is it that light is able to reach you? Well, the light that you're seeing is the light that hits your eyeball. The light initially is going out in every which way out of this bulb, and some of that light hits you. Okay, and it's just whatever light happens to hit you. Now, that light hits you and it scatters off in every which way. But let's say that you are seeing your tummy with the mirror. The light that you're seeing is light that has bounced from the light bulb onto you, then bounced from your tummy to the mirror, and then bounced into your eye. Okay, so seeing that go, it's not super profound, but there are a couple different steps that occur. Let's think about another question here. Let's say that you are you're sitting here on the edge of a lake. Again, there's my romantic picture of a person as an eyeball on a stick. Now you go ahead and you see a fish. And I'm asking the question, does the fish appear to be deeper or shallower than it actually is? Well, when I say that, I presume that you, as a person who's lived in the world, implicitly understand all of these rules for ray tracing. And so you assume that when you look at a poster on the wall or whatever, you're presuming that the light rays are coming in a straight line from the poster to your eyeball. And so when you look under the water and you see that fish, you presumably are going to simply trace that line the way that you normally would. But if we think about Snell's law and think about what's happening with the angle, light is traveling faster in air than it is in the water. So this light is actually traveling like that to get to your eyeball. And so the fish, turns out, is actually deeper than you would expect. And from what I understand, people who get good at spearfishing, for instance, have to learn to accommodate for this. So they aim underneath the position where they would naturally just look for the fish. All right, so let's quick look at a homework problem that we'll do with Snell's law. It says light in a vacuum is incident on the surface of a glass slab. Okay, so it's coming in at some angle. In the vacuum, the beam makes an angle of 32 degrees with the normal. To the surface, and notice I'm defining that with respect to this line that's perpendicular to the surface. That's what we mean by the normal. While in the glass, so here's vacuum, and here is glass. In the glass, it makes an angle of 21 degrees with the normal. Okay, so notice in the glass, the index of refraction is going to be higher because the light is going slower with the normal. What is the index of refraction of the glass? Well, here I have n of the vacuum sine angle in the vacuum equals n in the glass sine of the angle in the glass. So, in the vacuum, I know what the angle is. What would the index of refraction be in the vacuum? Well, V equals C over N. So the index of refraction would be equal to C divided by V. But in vacuum, the light wave is simply going at the speed of light. So N would be C over C equals just 1. Okay, so our N in the vacuum is just 1. And our N in glass is going to be something larger than 1. And so here, I can go ahead and put in my numbers. I'm not going to put in numbers right now, but I will show you how to do the expression. If I take my both sides and divide them by N glass, Ng, that would give me sine angle of glass equals NV, whoops. Let me not be crazy. We want to we want to find the index of refraction of glass, so all I have to do is find Ng. So that's easy in this case. I will just take NV sine angle V and divide it by sine angle G. And so of course make sure if you're given equations with degrees in them, make sure you're putting them in your calculator with degrees. Okay, now here's a slightly different idea. It says the index of refraction in benzene is 1.8. So benzene is a it's a clear liquid sort of like water. So let's think it's going to look sort of like this. You've got an N equals 1.8. What is the critical angle for a light ray traveling in benzene towards a flat layer of air above the benzene? So up here, the index of refraction is 1. And what do they mean by critical angle? Well, you'll notice if you look at this picture that somewhere in between this angle and that angle, you're getting a situation where none of the light is really going through. And that is called total internal reflection. And when that happens, the sort of the borderline between that happens when your angle in air is equal to 90 degrees. And so in that case, you would call the angle here your critical angle. That's when you're going like this from a smaller angle to 90 degrees. And so none of the light effectively is getting out, and that's the smallest angle that you could have for that condition. If you have any larger angle, all of that light will be reflected back. And so here we've got the index of refraction for benzene is 1.8. What is the critical angle? So you are simply going to put in your N in air, angle in air is 90, N in benzene is 1.8, and we're going to find that critical angle. And so if we set this up, it would be N air sine angle air equals N benzene sine critical angle. You hear that we've got a lawnmower going in the background. So how would I untangle this to get my angle? Well, I would need to divide by NB, and then I still have sine angle C, so I'm going to have to take the inverse sine of both sides. So my critical angle would be inverse sine of NA over NB times sine of 90. Now, sine of 90 degrees is just 1, so this would allow me to say that my critical angle is just the inverse sine of NA over NB. Okay, and in fact, for this case, NA is just 1, so this would just be 1 over the index of refraction of my material. So I'll let you put in the numbers for that. Now, why is this so useful? Well, the reason that we are very interested in this sort of thing as human beings living in a technological world is because we've learned how to use these very basic properties, Snell's law and the law of reflection, to make very complicated systems. So for instance, we have curved lenses that allow us to make sure that the images show up on the correct place in the back of our eyeballs. That's very useful. We've figured out, I mentioned the camp stove, where you focus light onto a focal point. So these are all examples, and let's just look at the simplest cases. Okay, we're going to think about spherical lenses and spherical mirrors, and to get a grasp on this, we think about a focal point. Now, the focal point is sort of easy to find if you have an actual mirror, because you take a faraway object and then you adjust the screen until it looks like you've got a pretty nice direct point of light from that faraway object. And that might seem like a sort of a little magic trick. And the same thing happens with if you have, for instance, a double convex lens. You can do the same thing. You can go outside, take the lens, put it up, and then take a piece of cardboard and try to see where you can get the image of the sun to be a nice sharp point. And that will be the focal length. That's the focal length, because all of those light rays are coming in to a single point. Now, what do we actually mean by that focal point in physics terms is that all of the rays from the same direction are mapped to the same point. So in terms of those faraway objects being imaged to the focal point, it's just that you have all of these parallel light rays from something far away are being imaged to a single point. If you had all your objects, all of your rays that were coming in at 30 degrees, for instance, they would all also get to a single point in what we call the focal plane of that mirror or lens. Now, why is that useful? Now, just to hammer it home again, there's nothing magic happening in these objects. This is just the law of reflection. Angle in equals angle out. You're just being a little bit clever with it. Again, there's nothing magic happening here either. It's just that you have two different interfaces and you're using Snell's law at each interface. So light comes in, light bends a bit, light goes out, and light bends a bit at the interface. But overall, by having those two different interfaces in the lens and a nice curved regular interface for the mirror, you can get nice effects for imaging. So, as a good way of thinking our way through this, we're going to look at a couple examples of what we call ray tracing. And here are the three rules that I'm going to try to focus on for ray tracing. Rays that come in parallel go in parallel to this optic axis, go out through the focal point. Rays that come in through the focal point, so if you went like in through here, they go out through the optic axis. They go out parallel to the optic axis. And depending on whether, we can call this focal length positive or negative depending on whether it causes the rays to come together or go apart. So this would be considered a positive focal length because it's causing the rays to come together. Okay, so where would you have a positive focal length for a mirror is when it is going to be on the same side of the mirror as the light. On the other hand, for a lens, this double convex lens is considered to have a positive focal length because it's causing these rays to come together over there. So converging rays have a positive focal length. On the other hand, this would be considered a negative focal length. It's on the opposite side of the mirror from where the rays are because it's causing those rays to spread apart. Same way with this double concave mirror. The rays are spreading apart, so the focal length that we consider is negative. It's spreading those rays apart. So negative is diverging, negative focal length is diverging, positive focal length is a converging lens, mirror or lens. So let's show a couple examples with ray tracing. Okay, so what are our rules? If our ray, so rays from all, this is our little object, and we want to see where the image of this object is. So that means where could I take the light that's bouncing off of this object and focus it on a little screen. So here, the way I could do that, there's light rays coming off in all different directions off the tip of this, but the ray that I'm interested in is the one that goes parallel to the optic axis. So if it comes in parallel to the optic axis, it's going to go out through the focal point. On the other hand, if it goes in through the focal point, so these are just two different specific rays that are coming off of the tip of my little arrow there. They're not particularly special, but they are useful. Okay, so come in through the focal length, go out parallel to the optic axis. Now this might not seem to give us much information, but actually it does. And where these two cross is essentially where the image of that little pointer is. And it turns out that if we did all of the other points on this, we could also find out where they are imaged to, and we would end up with a little image of a pointer that is upside down. So this is a real image because the rays are coming together, and I could focus that on a little screen, but it is inverted. That means it's upside down. Let's try another example. Okay, now this is again a positive focal length. It's a mirror that causes the light rays to come together. Let's see how it differs from our last example. Now I have a little pointer that's closer to the mirror than the focal length. So I go in parallel to the optic axis, and then I go out through the focal length, out through the focal point. Now, you might wonder, how am I going to go into the focal point? If I go in through the focal point, I'll just keep going out forever. So we're going to come in the direction of the focal point. I'm going to extend my mirror a little bit. So in the direction of the focal length, and then out parallel to my optic axis. Now I want you to notice something. These two lines are not going to converge. So there's no real image. There's no screen that you could go and put it in a place where you could focus that image. However, if you look into that mirror, you are going to see an image of the little pointer. And in fact, the image of that pointer, we're going to do exactly what we did at the very beginning, where we traced the lines back behind the mirror. And this becomes the pointer of that arrow. And again, I could do this with every single point on that arrow. And if you look into the mirror, you see an image of the pointer. Now, that's not an image that you could project on a screen, so we call that a virtual image. And it is upright, because the arrow is pointing in the same direction as the arrow. Okay, now this can also be used for ray tracing in lenses. Now, this is a converging lens. This is a double concave lens, and it's going to cause the arrow, the light rays to come together. So in this case, if I come in parallel to the optic axis, it's going to cause the light rays to go out through this focal length on the other side. It's causing the rays to come together. On the other hand, so in these cases, it sometimes is easier simply to go straight through the middle. So that's a possible one that you could also use. Okay, so that would be our image. Now you might ask yourself, okay, but what about the one where you said I could come in through the direction of the focal length and then go out parallel to the optic axis? Well, for lenses, it would be in through the back focal length, like this, and then out parallel to the optic axis. So it still works. It still works. It's just a little bit easier sometimes to just go right through the middle, as that's another one that works. In this other case, this is a double concave lens, so this diverges the rays, and so this back focal length would be the one that we would be concerned with. The focal length would be negative, and so I would come in the direction of that focal length, and then I would go out flat, and then I could again go in through the center and then just keep going. So those two are, these rays are never going to meet. So in this case, you would have to trace back those rays to some common intersection point, and this would be your image. So if you can imagine looking through this lens, you're not going to focus this image on a sheet back here, but you could get a virtual image here. This is a virtual image, and it is upright. Okay, so just to summarize that again, images that can be projected are real images. So here we have images that have a positive distance in the way that we count them. So here's our example of a real image. The light rays are coming in, they're bouncing off any which way, but all of the light rays that are coming onto this mirror are focused to the same point. It goes from one point here to one point in the image. Now, there are very particular points where sometimes you can't get an image, like if you put the object at the focal point, all of the rays are going to leave out in parallel, so you wouldn't get an image there. So that's a real image. This one is a virtual image, however. Images that cannot be projected are virtual images. So here's your real, there is your virtual. And it's virtual because you have to, with your eye, trace back those rays to some common origin. And so there's a little bit of a psychological effect. So here, again, this one is real because the images, the light rays are going to a single point. And here, these are virtual. Because the rays are not coming together, but if you look at that, you will see an object through that lens that's smaller and upright. So if we have a virtual image, they have a negative distance, either in front of the lens or behind the mirror. If you have a real image, we consider those to have a positive distance, which would be behind the lens or in front of the mirror. So that would be where you, in the space where you could project that image. Now, it turns out there is a quite nice relationship for these different distances and focal lengths. And what we do, let's say that you have an object here at some distance, and unfortunately the letters that your book uses are a little bit different from my picture, but this is the distance D, that's the distance to your object, and then you have a distance to your image, and that would be I. And if you have 1 over, P, 1 over P plus 1 over I equals 1 over F. Okay, so in this case, the F that you have would be positive in this particular picture. So that would be your F. And these three are related to each other. And as you can see, this is just a riot of, triangles. You can use similar triangles and prove this relationship just with geometry. I once spent an afternoon doing it. It's a little bit trickier than maybe it's worth us going through it. But as you can see, there's some interesting relationships here with similar triangles that you can use to prove this relationship. Now let's see, how would you use this relationship? Well, it turns out that there's what's called, this is the thin lens formula, and this is called the lens maker's formula. And it says a lens is made of glass having an index of refraction of 1.5. Okay, so that is our N. One side of the lens is flat and the other is convex with a radius of 20 centimeters. So how does this work? Well, we put the lens at x equals 0. One side is flat and the other has a radius of 20 centimeters. Okay, so this is a little bit hard to see, but you have to think about the circle that makes up each one of these. And for the R, we're going to put in what is the position of the circle on this X. So for this example, if this is flat, to get a flat surface, you'd effectively need to put your circle out at infinity, at plus infinity. So my R1 would be infinity. My R2 here would be 20 centimeters. Okay, so my R2 is going to be 20 centimeters. And in fact, because it's back here behind in the minus x position, I would put my R2 as equaling minus 20 centimeters. Okay, so for part A of this homework problem, I want you just to find that f. So it's a little bit of algebra, but I think you can do it. For part B of this homework problem, it says if an object is placed 40 centimeters in front of the lens, so your eye, and by the way, this is minus, you should find, so in A you're going to find f, and it should be positive. It should be a positive number. And then in part B, it's asked if an object is placed 40 centimeters in front of the lens. So that's like this. Okay? The rays are going to come together, and you are going to find where the image is. Okay, so you want to find I. I have given you P. P is 40 centimeters, and you have found F in your first part. Okay, so I want you to struggle a little bit, work on it, try to see if you can solve this just using your everyday algebra. So try that for next time. Now, this is, if you're wondering who cares, why does this matter? Well, it turns out we can use images and lenses to change the magnification of objects. So what do I mean by magnification? I mean the height of the image divided by the height of the initial objects. Now, the magnification can be either positive or negative. If it's upright, it's positive. If it's inverted, it's negative. And this equation has a minus sign because often you have upside down images. This is what happens, for instance, if you've ever seen what happens in a film camera. The film shows an image that's upside down from the light that's coming in. So I want you to try a little problem with that for next time too. It says a movie camera with a single lens of focal length 75 millimeters. So F equals, and everything here is in centimeters, and something is in meters, so let's just put everything in meters. So 0.075 meters. That's the focal length. It takes a picture of a person standing 27 meters away. So here's your lens. You have some focal length that's very short, and the person is far away. So here is your distance to the person. There's your P is 27 meters away. So using this equation, you can find out what your eye is, and you should find an image that's upside down, and I'll let you find out where it is. Okay. Now, it asks, if the person is 180 centimeters tall, what is the height of the image on the film? Okay, so once you find that I, you can find the magnification, and the magnification is just the height of the person, the height of the image over the height of the person. So the height of the person is 180 centimeters, so that's 1.80 meters. So you're going to use this. You're going to find that H prime. Okay, so you're looking for how big that image is on the film. Okay, so I'm going to let you work on that problem for next time too, and we'll see how it goes. Okay, so what have we learned? We learned that geometric optics ignores light's wave qualities, just treats it as rays traveling in straight lines. The lights bounce off of surfaces. That's our law of reflection for mirrors. In refraction, they're bent at material interfaces, and these lens formulas help us to predict how images are made with thin lenses and curved mirrors. All right, so thanks for watching.